Hello and welcome to this presentation related to thick cylinders. This is actually the fourth presentation in the thick cylinder lecture series. In lecture 1 we outline the proof related to Lamè's equations that we use to solve problems involving thick-walled vessels. Lamè's equations are repeated here for reference. The radial stress equation, denoted as sigma r within our presentations, is equal to A minus B divided by r squared, where r can be any radius between the inner and outside vessel wall, and the hoop stress equation, denoted as sigma h, and sigma h is equal to A plus B divided by r squared. In our second presentation, lecture 2, we considered an industrial case study analysing a thick-walled hydraulic cylinder, where we calculated the radial and hoop stresses throughout the vessel wall, and lecture 3, we considered further questions associated with application of Lamè's equations. It is strongly encouraged that you review the 3 previous presentations before reviewing this presentation. So here's an overview of the presentation. We commence with a very brief recap of the previous solutions, which involves the generation and solution of simultaneous equations to help us find the radial and hoop stresses through the vessel wall thickness. And we also review the reference source we're going to use and the Pince's presentation. This is Formulas for Stress and Strain by Roark. I'm actually going to use the second edition within this presentation, and that's dated from 1943. The object of this presentation is primarily to prove the formulae stated within Roark's Formulas for Stress and Strain. So we commence by reviewing a proof of the radial stress formula, shown here on the right hand side. It uses slightly different notation to that shown in Roark's Formula for Stress and Strain, but essentially the same formula. And we very briefly show proof of the hoop stress formula, and we derive this formula for hoop stress, which is essentially the same as that for the radial stress, except the minus sign in the numerator of the radial stress becomes a plus sign in the numerator of the hoop stress. Then we provide a summary of the formulae between our reference source and our derivations to show essentially they're exactly the same. Then we revisit question 2 from our previous presentation. This is a thick cylinder with internal pressure only. We solved this in the previous presentation by generating simultaneous equations. Here we're going to solve it using the standard formulae shown above for the specific case. And finally, we review question 5 from our previous presentation. This has both internal and external pressure, and again we solve it using the standard equations derived in this presentation. You'll see from the solutions presented for questions 2 and 5, the derived formulae are very accurate. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are rounded to the nearest minute. Here's a recap slide from a previous lecture, which shows the method of solution within all the problems solved was to use Lamè's equations to generate 2 simultaneous equations and solve for the unknown constants A and B. I encourage students to use this method throughout all questions because it helps practice their mathematics, as also shown an application of mathematics to solve a mechanical principles problem. Here's a recap slide of Lamè's equations, showing an enlarged view of the equations. However, within practice, engineers would not solve the problems using the simultaneous equation methods. Within a design office undertaking hand calculations, engineers would refer to appropriate reference sources, where they would find specific formula for calculating the radial stress and the hoop stress within the thick cylinder wall. The reference source I'm going to refer to in this presentation is known as Formulas for Stress and Strain, and it's by Roark. This is a very standard industrial textbook that many design engineers and stress engineers will refer to, and is a valid reference they can quote within their reports. Here I'm actually referring to the second edition of this book. It's actually published in 1943. It's a copy a senior engineer gave me many years ago. There is obviously a more up-to-date reference source, but the actual formulae will be stated in a very similar manner, as that's shown on the following slides. This is not a lecture I directly deliver to students, although I do emphasise that in practice there are standard reference sources engineers use to calculate stresses within a thick cylinder wall. And purely for background interest, if you would like to read the preface associated with the first edition of Roart's Formulas for Stress and Strain, I've included it here on this slide. It's continued on the next slide. Preface for the first edition continued here. This was actually August 1938. And here's the preface to the second edition. That's the reference source we're using to underpin this presentation. Again, this is purely for your interest. So here's an extract from Roart's Formulas for Stress and Strain. And here are the actual formulae I'm going to refer to. Within this presentation, the case I'm considering refers to uniform internal radial pressure in pounds per square inch. In 1943, the imperial units were used within industry, and it states that the longitudinal pressure within the wall is zero or externally balanced. So we're just purely considering the radial and the hoop stresses within the cylinder wall. The notation used for thick vessels in Roart's book states that S1 is the meridional wall stress, that's the longitudinal wall stress. I'm not interested in that within this presentation. S2 is the hoop wall stress, and S3 is the radial wall stress. Notations for positive stresses are shown within the figure here. Note within the sketch shown here, our reference source shows that tensile hoop stresses are positive, but compressive radial stresses are positive. Within the derivations that follow, we will use the same notation for hoop stress, but radial stresses in our derivations will actually be tensile positive. So essentially within this presentation, I'm going to show you how we solve for these equations, which allow the various stresses through the six-cylinder wall to be calculated without resulting to generating and solving simultaneous equations. As I said, I do not encourage my students to use this method, but I do sometimes suggest that they can check their answers using these formulae. Here's an enlarged extract from Roart's Formulas for Stress and Strain. From the notation, S2 is the hoop wall stress, S3 is the radial wall stress, symbol A is the inner wall radius, shown here on our diagram, and symbol B is the outer wall radius, shown here. The cylinder wall stresses, the radial stress S3 is denoted by this equation. Notice some students find the location of the P in this equation slightly difficult to understand, so I've rewritten the radial stress equation for S3 here, showing the internal pressure on the top line. Notice that variable R is the radius considered, which can be anything between the inside and outside surface of the vessel. Here's S2, the equation for the hoop stress through the vessel wall thickness. And again, I've just slightly rewritten the hoop stress equation S2, showing the internal pressure again on the top line. The reference source also states the maximum hoop stress, the maximum S2 here, given by this equation, as again I've rewritten the maximum hoop stress with the internal pressure on the top line. From our previous presentation, the maximum hoop stress occurs at the inside surface when we have an internal pressure only. Again, it should be noted that all these equations relate to an internal pressure only applied to the vessel. Let's commence by considering six cylinders subject to internal and external pressure. So we're going to generate a formula to calculate the radial stress through the vessel wall when we have both internal and external pressure on our cylinder. Notice the notation used here is that used in the previous presentations. Our I will be the internal radius, our O will be the external radius. So we commence the solution by considering the internal radial stress. That will be negative pi, and that's equal to A minus B divided by Ri squared. Given these equations labels that continue from our previous presentations. The outside radial stress is negative PO is equal to A minus B divided by RO squared. Equation 15 for reference. So we're using the radial stress equation here to generate these two equations. I'm now going to subtract equations 14 and 15. So that gives negative pi plus po is equal to negative b divided by ri squared minus, put it in brackets here for clarity, negative b divided by ro squared. So notice by subtracting the equations, the constant a is eliminated from the solution. The rest of the solution is purely algebraic manipulation to find constant b. On the next line there's a change of sign here. Then we factorise on constant b, just reorientated the fractions inside the bracket, the positive 1 upon ro squared first minus the 1 upon ri squared. Next we have a common denominator, so the numerator is ri squared minus ro squared. Some students do struggle with the use of fractions here, so I just tried to elaborate this using two-line formatting, so that's clearer for you to understand. Our next line we simply rearrange for constant b, so in other words we multiply throughout by ro squared ri squared, and we divide throughout by ri squared minus ro squared. For the final line here, just remove the bracket from this term here, so constant b is given by equation 16. As our thick cylinder is subject to internal and external pressure continued, just repeated equation 15 for convenience here, and also equation 16 from the previous slide. And now we're going to substitute equation 16 into equation 15. So here's constant b, equation 16, being substituted into our equation 15. Notice on the right hand side here, instead of dividing by ro squared, I'm multiplying by ro to the negative 2. Just doing that for my convenience. On the next line, I've simply cancelled the ro squared in the numerator with the ro squared in the denominator. So the expression here is simplified. And finally, we arrange for constant a, and in this case, we simply add this expression to both sides of the equation. And I've labelled that as equation 17 for reference. Thick cylinder is subject to internal and external pressure continued. Just repeated the equation for constant b, labelled 16 here, and for a, labelled 17, and also the radial stress equation, equation 12. The label 12 is a reference to a previous presentation. We're now going to substitute equation 16 and 17 into equation 12 for our radial stress. So here's equation 17 for constant A, here's equation 16 for constant B. So our radial stress equation is equal to A minus B, and it's all divided by r squared. Notice I've written that as r to the negative 2 here for my convenience. On next slide, just slightly rearrange the equation, just move the r to negative 2 to here. Notice on this line on the right hand side there are three terms in the expression. The first and the third have the same denominator, so on the next line I formed a common denominator here. On the next line I've factorised on this term here, as it's common here, here. And on the next line I have a common denominator of r squared for this particular bracket here, just slightly rearranging the format. So on the final line of this slide we have the radial stress equation is equal to pi minus po multiplied by ri squared, that's divided by ro squared minus ri squared, and that's multiplied by r squared minus ro squared divided by r squared, from which we then minus the external pressure PO. Label that as equation 18 for reference. And just note how the terms in this bracket here have been reorientated, as have the terms in this bracket here. So it doesn't affect the overall equation, but the final orientation of equation 18 is aligned to the formula in the standard reference source we're using. Thick cylinder is subject to internal and external pressure continued. Just repeated equation 18 from the previous slide purely for reference. So now if we consider the outside pressure to be 0, i.e. PO is equal to 0, the radial stress equation simplifies to equation 18a here. In other words, we've removed this term and this term from equation 18, and equation 18a can be rearranged into this form, which is akin to that shown in our reference source, so I've labelled that as equation 18b. If we now consider the maximum radial stress when PO is equal to 0, we find it occurs at the bore, so now radius r is equal to Ri, the internal radius, and equation 18b simplifies to equation 18c to calculate the maximum radial stress. And of course we know from our previous presentations that will be equal and opposite to the internal pressure applied. That's found because the numerator divided by the denominator has a value of -1, hence the answer of -pi. Let's now consider thick cylinders subject to internal and external pressure. Now we're going to generate a formula to calculate the hoop stress through the vessel wall. The equations 16 and 17 stated for reference. I've also stated equation 13 from our previous presentation. It's a very similar process to derive the equations hoop stress as for radial stress. We substitute equations 16 and 17 this time into equation 13 for the hoop stress. I'll let you review the solution at your own pace, from where the hoop stress is given by this equation shown here. Label the equation 19 for reference. Notice the hoop stress equation 19 is identical to that of the radial stress shown here, equation 18, except for this minus sign here. Here's the plus sign in the hoop stress equation. Thick cylinders subject to internal and external pressure continued. Just repeated the generic hoop stress equation 19 here for reference. And again, as previously stated, we can now consider the outside pressure to be 0. PO is equal to 0. So equation simplifies to that shown in 19a. And I've just rearranged 19a into the standard forms that's used in the reference source in 19b. Note when the outside pressure is 0, the maximum hoop stress occurs at the bore, so R is equal to Ri. So this is the formula for the maximum hoop stress in a thick cylinder vessel wall when there's only internal pressure applied. Label that as 19C for reference. So here's now a brief summary of our thick cylinder wall stresses, comparing the formulae extracted from our reference source, Roark's formulas for stress and strain, with the formulas we've derived in this presentation. Note there are slight differences between our reference source and our derivations. In the reference source, the inside radius of the thick cylinder is labelled as A, and the outside radius is labelled as B. But in our derivations, we've used the same notation in this presentation as in the previous presentations, so that's Ri is the inner radius, Ro is the outer radius. Now, the case we're using from our reference source assumes that the outside pressure, PO, is 0, as do the derivations also assume that there's no external pressure acting on our thick-walled vessel. There is a difference with regards to the radial stress. In Roark's formulas for stress and strain, a compressive radial stress, denoted S3 here, is deemed positive, whereas in our derivations, a tensile radial stress is positive. It doesn't really matter that there's a change of sign in the radial stress between the reference source and the derivations, as long as we're aware of this when we use the appropriate equations. If we now compare the radial stress S3 from our reference source to the radial stress sigma r we've defined, they're essentially the same formula. They use different notation, but notice on the top line, because of the difference in the senses of the radial stress, the numerator here has the outside radius minus r squared, whereas our derivation has the r squared minus the outside radius squared. That's probably due to the different notations used for the radial stress. Of course, the symbol r denotes any radius between the inside and outside surfaces. If we now consider the hoop stress, denoted S2, in Roark's formulas for stress and strain, we essentially have the same equation from our derivations, just different notations for the inside and outside radii. And if we consider the maximum hoop stress, the maximum S2, from our reference source, again, that's essentially identical to that we derived. Remember, with only internal pressure applied to the six-cylinder, the maximum hoop stress occurs at the inside surface at radius Ri in our derivations. So there's the equation from our reference source that we've now proved using our derivations. And purely to show the equations are valid, I'm going to refer from our previous presentation related to analysis of six cylinders. I'll show you the solution for question 2 solved using simultaneous equations and how the values using our standard formula are identical. So here's question 2. I'll let you review this at your own pace. As I said, it's from my previous presentation, worked through in detail. Here's question 2, the solution. Extract the information from the question. This was a six-cylinder because its D upon T ratio was less than 10, so Raman's equations are applicable here. Question 2, solution continued. Here's the generation of our simultaneous equations, in this case using the radial stress at the outside and the radial stress at the inside surfaces. We solve for the constants A and B. Question 2, solution continued. And inserting the constants A and B into the radial stress equation, we could calculate the radial stresses through the cylinder wall, outside, intermediate, position, and inside. Question 2, solution continued. And again, using the hoop stress equation, we calculated the hoop stresses outside, intermediate, and inside vessel wall. So here's question 2, solution, but now using standard formulae. I'm using the formula the outside pressure is 0, so we're going to calculate the radial stresses through the vessel wall using this equation. That's the equation 18a on our previous slide, because it shows how this value is actually a constant that we can evaluate once and just repeat its use. We can clearly see that the outside radial stress is 0, as it should be. The intermediate radial stress halfway through the thickness of the vessel wall is the same as that calculated previously, and at the inside surface the radial stress is equal and opposite to the pressure. This question 2, solution continued, again using standard formulae. So for the outside pressure is equal to 0, the hoop stresses are given by equation 19a on our previous slide. Again, I'm using this to show this is a constant here. And we can evaluate stress at the outside surface, halfway through the wall thickness, and at the inside surface. And again, we can see these are the same as that calculated from the simultaneous equation solution, shown here. And finally, from our previous presentation, here's question 5. This is a problem where we have both an external pressure and an internal pressure. Here's the solution for question 5 from our previous presentation. I'm going to let you review this totally at your own pace here. If you've seen the previous presentation, you will have seen the solution. Question 5, solution continued. Here's our generation of the simultaneous equations. You review this at your own pace. Question 5, solution continued. We derive equation for the radial stress, shown here in its simplified form, and the hoop stress, shown here. So we calculate the radial stresses through the vessel wall. Question 5, solution continued. We calculate the hoop stresses through the vessel wall. Question 5, solution. This just shows you a diagrammatic view of the variation in the radial stress through the vessel wall, and variation in the hoop stress through the vessel wall. Here's question 5, solution continued. This time using the standard formulae we derived. Firstly, for the radial stress, sigma r, using equation 18 on our previous slide. We know the internal and external pressures, so we can calculate the radial stresses. Let you review this solution at your own pace. As we'd expect, the radial stress at the outside surface is equal and opposite to the pressure applied at the outside surface. Question 5, solution continued. Again, using our standard formulae, equation 18 here. And we calculate the radial stress midway through the wall thickness and the radial stress at the inside surface. Again, the inside surface radial stress equal and opposite to the pressure applied. If we compare the stresses calculated using the standard formulae, the stresses calculated using Lama's equations and the simultaneous equations approach, they're exactly the same. Question 5, solution continued, and using our standard formulae. This time for the hoop stress, we're using equation 19. So working out the hoop stress here at the outside surface, compressive stress here. And question 5, solution continued, using our standard formulae, stress equation 19. We can calculate the stresses at the intermediate position and also at the inside surface. And here are the hoop stresses from our simultaneous equations calculations for comparison. So that concludes the presentation, which I hope has been of some interest to you, and as always, thank you for viewing.